Hello, my name is Chris Howerhan, and today I'll be providing a presentation on the paper Context-Free Attacks Using Keyboard Acoustic Emanations. First, I'd like to just call out the authors of the paper, and I apologize in advance if I mispronounce anyone's name, but we have Tong Zhu, Qiang Ma, Shanfeng Zheng, and Yunhao Liu, all from Tsinghua University in China. And this paper was originally presented at the 21st ACM conference on computer and communication security in Scottsdale, Arizona, back in November of 2014. So just wanted to provide a brief outline of the presentation. So I'll begin with the background and objectives, a little bit of context on the attack and the exploit. Then go into an overview of the attack. We'll walk through the workflow, including the pre-processing, time distance of arrival estimation, keystroke pinpointing, and keyboard reconstruction and keystroke recovery steps. And then we will evaluate the results of the experiments conducted by the authors of the paper, and then wrap things up with a conclusion. So using mechanical, electronic, and acoustic signals from keyboards and other devices is not something that's new. As early as the 1910s, German scientists eavesdropped on French field phone lines. In 1943, an engineer with Bell Telephone discovered electromagnetic signals by means of an oscilloscope while using a Bell Telephone Model 131B2, which was a top secret encrypted teletype terminal used by the US Army and Navy to transmit wartime communications during World War II. And researchers have eavesdropped on video display units by picking up and decoding the electromagnetic interference produced by the equipment. With the rise of smartphones that are increasingly becoming more powerful and more sensitive, attackers can plant malware into a target's smartphone that can automatically record the signals when a user is typing on a keyboard to recover the keystrokes and send that data to the attacker's server, computer, whatever. Most existing acoustic-based malicious applications assume that the typed contents are correlated, and they infer the content using machine learning technologies. You can think of this like your autocomplete on a phone, where it is guessing the next word based on the context of the previous words typed. This has some disadvantages, however. There's a high cost at the context learning stage to train the models. The assumption is not valid in many cases. For instance, passwords are random characters and numbers typically. And any mistype can affect the detection accuracy and does so that in a cascading way. Whereas if you misinterpret one word, then your subsequent words that you're predicting based on your models could be incorrect. So the researchers of this paper thought that by collecting the acoustic emanations from keyboard using off-the-shelf smartphones, they could determine the typed key's physical position in a geometrical way. And so for each pair of microphones, they measure the difference of distance range from the key to each microphone to estimate the position of the key on a 2D plane. Now it's important to note that the sampling rate of the microphones can affect the quality of this. Obviously, a lower sampling rate provides a lower signal and reduces the accuracy of the attack. And this also requires an initial stage where the keyboard location is constructed before capturing the input of the keystrokes. So basically the attack tries to be generalized in that it has no prior knowledge of where the keyboard is in relation to the phone. So a quick overview of the attack. As you can see in the top diagram, just an illustration of what I mentioned with respect to measuring the difference in distance of range from the key to the microphones. The sound wave is going to reach the top microphone before or after the bottom microphone, depending on where the keyboard is and what the key that was typed is. And using a time distance of arrival algorithm and multiplying that by the speed of sound, which is the 343 meters per second there. The algorithm can generate these hyperbolas that can basically give an estimation as to where the key was, what key was typed on the keyboard. And by using multiple smartphones, each one can generate its own hyperbola, which can be overlain to more precisely predict the location of the key. So that's a brief overview. We'll go into obviously more detail as we walk into the workflow. So the attack workflow, we'll go into the specifics of each of these, but just at a high level. There's 4 stages. There is the pre-processing stage where the acoustic signal is segmented into pieces representing a single keystroke, and those pieces are grouped across all microphones. Then there is an estimation stage where a generalized cross-correlation algorithm with phase transformation weighting is used to calculate the time difference of the keystrokes acoustic signals arrival at the different microphones, which then allows for the next phase, which is generating those hyperbola bands. Again, having multiple phones, the bands can be overlain to narrow down the candidate area of the key that was typed. And then finally, there's key reconstruction and keystroke recovery. And so after all these signals are collected over a period of time, the keyboard is reconstructed. The center of the keyboard and the rotational angle of the keyboard are reconstructed, and then subsequent keystrokes can be recovered based off of the keystroke pinpointing and knowing the layout of the keyboard. So let's walk into the pre-processing stage here. So the keystrokes are divided into essentially 2 events, press and release. And within those 2 events, there's actually 3 unique peaks or signals that the researchers were picking up upon. There's the touch peak, which occurs when your finger first touches the key, the hit peak, which is when the key actually gets pressed down, and then the release peak, which is when the key is released. The researchers focus on the hit peak, which, as you can see from the figure on the right, is the most distinct and conspicuous of the 3 peaks. The touch peak was too inconspicuous to utilize, and then the release peak was too drawn out to be able to utilize, making it hard to pinpoint and use as a signal. So once the algorithm takes in these acoustic signals that are broken up and then transforms them into energy signals. So they are taking a sliding window of 10 samples to calculate the accumulated energy based off of the raw acoustic signal picked up. And then the hit peak is the highest energy point identified over a period of 100 milliseconds. So why 100 milliseconds? Well, they set the search range to 100 milliseconds because the period of a keystroke from push to release is typically more than 100 milliseconds. And there's at most 1 hit peak during that 100 milliseconds. And so when a hit peak is identified, they take the preceding 10 milliseconds and the subsequent 90 milliseconds to form the signal representing a keystroke. And they do the 90 at the end because, as you can see from the signal above, the sample above, the release period is longer than the period preceding the actual touch event. So next comes the time distance of arrival estimation step. So um, here there's two signals. There's one from each microphone that are being used. One microphone is picked as the reference signal, and the second microphone is used as the sliding sampled signal. And with these two signals, a cross correlation algorithm is used to associate to identify the offset of that hit peak between the two microphones. The researchers initially used just a generic cross correlation algorithm. However, due to the reverberation effect on the signals, it made that standard cross correlation algorithm error prone because there was multiple inconspicuous peaks. So they applied a generalized cross-correlation algorithm that adds a weighting function, which provides a more distinct single peak of the signal. And you can see in the figure to the right, the lighter line and peaks are from the standard cross-correlation algorithm, and then the darker line and darker peak is from the generalized cross-correlation algorithm. So it has an advantage that it makes the peak distinct and clear by comparison. So with that time distance of arrival computed between the two microphones, it's possible to identify a candidate area for the key that was pressed by generating this half hyperbola band. And the researchers used actually a band versus just a single half hyperbola, which you can think of it as the band having an upper and lower bound on the hyperbola. So this provides for a degree of estimation error in the calculation. And so then the question then becomes, what is the width of the band that should be applied? If you have something that's too narrow, then you could be misidentifying keys. If you have something that's too wide, then that could lead to too many candidate keys, and you can't guess the key based on the keystroke. So the researchers proposed a conservative method according to the third quantile of the distribution measurement error as the width of the hyperbola band. And then, as I previously mentioned and alluded to, a single phone can be used, and you can see in the illustration here what that looks like. However, you can get greater accuracy if you're using more than one phone at a time because you can overlay the bands, which narrows down the candidate area so that there's less to consider in identifying the keys, and you can get a higher degree of accuracy. So next, the final phase is keyboard reconstruction and keystroke recovery. So as I mentioned earlier, the researchers wanted to make this attack generalized by not presupposing the position and orientation of the keyboard. The one caveat is that they do presuppose the layout of the keyboard. So outside of the scope of this paper was handling, various layouts. So they assumed a kind of a standard layout for a keyboard. However, the relationship between the phone and the keyboard in terms of position and rotation is not known to, again, make it more generic. So really with keyboard reconstruction, the goal is to identify the center and rotational angle of the keyboard. And therefore they're mapping the actual keyboard layout, which again is pre-known, onto a 2D plane, and then using these candidate areas for each keystroke to then map that to a key and recover the keystrokes. So there actually needs to be a period of time where the keystrokes recovered are used specifically for keyboard reconstruction. And the researchers evaluated how many keystrokes that should be, and ended up arriving at around 370 keystrokes, which balances accuracy with computational cost. There's actually a very high computational cost to doing the reconstruction because it requires looping through each of these events to basically identify the best possible fit based on those 370 keystrokes or however many keystrokes there were typed. So it is cost intensive. Um, but what they're doing basically is they're trying to identify the maximum intersection of each candidate area. And then using that maximum, using all of those maximum intersection areas, again, looping through each of those, and then looping through the key regions, which they ended up choosing to be not the size of a key, but actually a unit smaller than a key. So they divided the key into 4 equally sized key regions, which allows for the intersection to match boundary areas between the keys, since there's spaces between the keys on the keyboard. Um, so they're looping through each of those intersection areas and then looping through each of the key regions on the keyboard for each of those intersections. And the algorithm basically rotates and centers the key regions to match the intersection, and then lays out the keyboard based on that assumption, and then evaluates all of the other candidate areas against that, and then picks the rotation and center that has the maximum coverage for the keys recovered. So again, as I mentioned before, there's a high computational cost to doing this, but it provides a more generalized attack workflow. And once the center and rotational angle of the keyboard can be reconstructed, then all of the keystrokes can be mapped to the keyboard using a similar maximum intersection for the candidate areas, and the keystrokes can be recovered. And you can see in this figure, just to kind of help drive the point home, what that maximum intersection looks like. So it's the darkest area across each of these 3 pictures. And as you can see, with more phones, you get a tighter intersection that is more closely aligned with a single key to estimate which key was pressed. Um, so now we'll walk into kind of the evaluation of the experiments that the researchers conducted to test their idea and their algorithms. Again, they wanted to make this very generalized using off-the-shelf technology. So they had 3 Samsung Galaxy Note 2 smartphones running Android version 4.3. Each phone was equipped with 2 microphones, one at the top and one at the bottom. And each microphone had a sampling rate of 44.1 kilohertz. And they placed the phones in varying positions to the left, right, and above the keyboard. And actually, in a couple slides, I'll go through some of the evaluation that they did to identify the optimal placement of the 3 phones. They tested this on 2 different types of keyboards, an Apple and a mechanical keyboard. And they had 2 different volunteers participate in the experiment. So they each typed text from Martin Luther King's "I Have a Dream" speech. They didn't use any capital letters, so it was all lowercase letters. And then they included space, delete, and enter keys as well. The first volunteer had 3,372 keystrokes. The second volunteer had 3,452 keystrokes. And the average typing speed of the first volunteer was 577 characters per minute, and the second one was 321 characters per minute. So as we'll see from the results, the attack works with pretty fast typers here, with those falling into the average, and the fastest typers generally being 600 to 800 characters per minute. So let's look at the accuracy across the alpha characters. You can see every character was typed at least once with the exception of the character Z, which wasn't typed. The character E was the most typed letter with 337 and 350 keystrokes between the two volunteers. The average accuracy for that letter was 78.1% with 268 and 269 keystrokes recovered respectively between the two volunteers. So fairly high. For space, enter, and delete, there were 597 instances of the space key being pressed and 32 of the enter by the first volunteer. And their approach recovered 85.8% of those keystrokes. And for the delete key, they were able to recover 70 out of 78 keystrokes for a recovery rate of 89.7%. So the researchers also took the results of their evaluation and generated a heat map, which you can see on the keyboard to the bottom right, where the darker the key, the more accurate the recovery rate was, and the lighter the key, the less accurate the recovery rate was. And you can see they also plotted the keys from the highest to lowest in terms of accuracy above there. Overall, they achieved an accuracy of 72.2%. And their highest, you can notice that there are certain keys that are more highly identified than other keys, and they went into a little bit of why that is. So the highest accuracy keys tend to be keys that are located on the edges, or those keys that are larger than others, like the space, enter, and delete keys, which also happen to generally be on the edges. So the larger the key is somewhat intuitive. There's just more area for them to identify that particular key compared to other keys. For other keys like E or T, those appear at the edges at the top, and those can be more accurate because the candidate area of the hyperbola bands and the key coverage area is smaller. So they're not considering any key coverage that lies outside of the zone of the keyboard. And since they're only considering the alpha characters, anything above, the number of characters above the E and the T are not considered, and therefore there's less of a coverage area and, again, higher degree of accuracy there. Also, the key frequency also played an effect. So you'll note that Q and W are also on the edges of the keyboard, but were not as accurately identified as the character E. Well, Q and W tend to be typed less frequently than the character E or T. And since those characters are typed more frequently, they have more candidate areas to narrow down the maximum intersection and pinpoint the key that was typed based off of the acoustic emanations picked up. The researchers also wanted to test their approach with some background noise. So they tested it in 3 situations: a quiet library, an office bustling with people, and a noisy meeting room. And they varied the experiment a little bit. They had the words "Hello World" typed 100 times in each situation and tried to recover each keystroke. And their approach achieved detection accuracy of at least 64% in these noisy rooms, with more than 83% of the character space recovered, even in the noisy room. As I mentioned before, the researchers played around with some different orientations of the phones with relation to the keyboard. So they had 3 phones in 5 different possible positions, and you can see the kind of the heat maps of those hyperbola bands generated from each of those positions. And they found that position E with the phones in the 1, 3, and 5 areas worked the best. And this is in contrast to like phones oriented in positions 1, 2, and 3, which has more than half of the maximum intersections are close to each other or cover several keys, which degrades the accuracy of the keystroke recovery. They also played around with rotation. They modified the angle of smartphone 5 and rotated it 45 degrees and 90 degrees. And then when they rotated the phone 90 degrees clockwise, you can see most of the intersection areas are more concentrated and therefore better than 45-degree rotation. So in conclusion, the geometry-based approach utilizes this time distance of arrival technique to calculate the relative positions among keystrokes and microphones equipped on standard smartphones. This is different from previous approaches in that it's not dependent on the correlations between the contexts being typed, and it leverages commodity smartphones. And it also is able to perform under randomly typed content, such as passwords. And overall, the researchers were able to achieve an accuracy of 72.2% in key recognition. That concludes my presentation. Thank you.